All right, we'll start. The I have to send a new link since the link expired. So from today onwards, you can use this link. It will be valid for next 10 weeks. Right. Uh, so we were looking at the simple random spatial sampling. Can you all hear me?
Yes, sir.
Right. Okay.
Yes, sir.
We were looking at simple random spatial sampling. So we were looking at uh, out of available number, how many samples we can take. So when we take samples, uh, if we have like 100, uh, 1 hectare research field and select 100 samples, how many sample possibilities exist? So we look at the equation, how to calculate it. So if the sample number of samples, uh, we use factorial combination. Anybody who remember the equation? Anybody? If the number of sampling locations available is m and number of samples you select is n, m and n, what is your equation about how many sample possibilities exist? M factorial divided by m minus n factorial. Remember? Right. Okay. Now I will give you example. If there are 1,000 sampling locations, no, if there are, sorry, we'll take it a smallest example. If there are 25 sample locations and we want to take 20 samples, how many possibilities exist? Total number of samples is 25 and we are going to take 20 samples at a time. How many possibilities exist? Can you send the answer through chat? Only one person replied, one answer. Only Kavipriya. Bruce, can you check your answer again? It's not correct. Okay, we are taking a lot of time. 24086 is not correct answer. I got three answers, all three are different, but there's one right answer. I think most of you have not got the answer right. So I'll go back to this combination A, B, C, D. There are four samples. You can either take A, you can take B, you can take C, and you can take D. Right? So when this is the situation, if you take two samples, how many combinations exist? Now look at when you use the, you can use combination AB is possible, then it's possible AC, and it's possible AD. Then it is possible to have B, AB, AC, AD, BC, and then you can have BD, and also you can have CD, right? So these are your combinations. So how many combinations you have? 6. So if there are 4 sample locations and you are taking 2 at a time, you can take 6 combinations, right? If you are taking as A and B and A is 2 different combination. There are certain location times A and B is something, B and A is something else, right? Then you have 12 opportunities, right? Now take the example, you throw a die. You know what the die is? The 6-sided uh, box that you use for gambling, right? So where you have 1, 2, 3, 4, 5, 6 numbers on the 6 sides, or 3, 6, 9, 12, 15, and 18. So suppose we have that. So I will draw the, sorry. So I will draw the other 2. Right? So A, B, C, D, if I number this is E and this is F. So instead we can number here, we can number 3, we can put 6 here, and we can put 9 here, we can put 12 here, 15 here, and 18, right? So this is the kind of a die that you throw, right? So 3, 6, 9, 12, 15, 18. There are 6 sides of the die that you throw, and then any side is possible if it is a equal chance, uh, equal sided die. So when you throw it, you get either 1, 2, 3, 4, 5, 6, or 3, 6, 9, 12, 15, and 18. Now, so how many sampling opportunities you have? You can get any of the 6, any of the 6, right? And then if you do it, if you throw it twice, what are the combinations possible? You can have, if you throw it twice, you can have 3, 3, you can have 3, 6, you can have 3, 9, you can have 3, 12, you can have 3, 15, you can have 3, 18, and then you can have 6, 9, you can have 6, 12, 6, 15, 6, 18, then 9, 12, 9, 15, 9, 18, then 12, 15, 12, 18, 15, 18. So how many combinations you have altogether? How many combinations? So your total number is 6. You take 2 out, right? You take 2 out at a time. So 6 factorial, 6 into 5 into 4 into 3, and then you take 2 out, 2 into 2, 4. So 6 into 5, 30, 30 into 3, 90, 90 into 2, 180, 180 divided by So you have 45 combinations possible if it is both sides. If we take all six in one go, so what you have is six, only one opportunity exists. If you take five at a time, you can take like 3, 6, 9, 12, 15, or 3, 6, 9, 12, 18. And then you can have uh, leaving 6, 3, 6, 9, 12, 15, 18, or you can have leave uh, 6 out. Likewise, you have several opportunities possible. So this is the sampling opportunities. So when you have the sampling opportunities, that decide the outcome frequency. Like when you toss a coin, you have two sides, right? Head and tail. So your opportunity of getting one side is 50%. We say probability by dividing all possible events out of the event that you want to have. If you want to have the event head, it's 1 divided by all possibilities is 2, 1 over 2. So likewise, when you have large number of sampling locations and when you take different number of samples, what is important is to look at the probability of getting something. You need to you need to have understanding of total number of opportunities possible, right? Total number of opportunities possible. So that's the kind of so if you look at these combinations, what is possible, if you take 2 out, AB, you can have AC, you can have AD, and then you can have AE and AF before going into B, right? So when you have AB, AC, AD, you have total number of points minus 1 is the available number of combinations you have. So you have 6 minus 1 is 5 combinations possible. When you go to B, you have possibilities for 4 combinations. So 5 plus 4 combination, 9. Then 3 combinations, 12. Then 2 combinations, 14 plus 1. So altogether, 5 plus 4 plus 3 plus 2 plus 1, 15 opportunities available. Okay. When the other issue is, when you take now A and B, the uh, when you take first time A, B, next time when you throw again, A can happen. The possibilities A is there because you don't remove that. You don't remove that from the sample. But sometimes your sample is destructive, right? When you take sample A and B, and next time you can't take A and B. Suppose you have physical samples, you cannot take A and B once again, once you take it. So that is when the population is finite, limited number. Once you use it, you cannot use it. But the relationship is different when the population is infinite. So that says sampling with replacement and without replacement. Sampling with replacement and without replacement will have totally different probabilities. But when the population is infinite, then with replacement or without replacement will not matter. I'll take example, right? I'll first erase this, take this easy example. Right. Now, if you have this 4 A, B, C, D, right? Now, when suppose you have A, B, C, D, 4 plants. One is A plant, second one is B plant. So once you take the A and B sample, A and B is gone, right? So what is available for you to sample is C and D. So how many combinations you have? Only two combinations. Either you can have A and C, you can have A and D, you can have A and B, right? Once you take that, that opportunity is gone. Then next opportunity is other two. So if you take out of this without replacement, if you take, you can have only two samples, two combinations, either AC, AB, or AD, then whatever the balance two. But if you have replacement, once you take A and B, your A is still available, because once you take A and B, somebody else will put an A and B plants again from the same place. Then you can have A and C, and then you can have A and D. So with replacement and without replacement, your opportunities, number of possibilities, your probability values will change significantly. Okay. So when you talk about the like sampling in a lake, you measure temperature. So there's no problem of replacing. Once you measure the temperature, it will not affect the next measurement. Right? So it is like sampling with replacement, because when there are infinite number of places where you can take the temperature measurement, your temperature measurements are having infinite number. So then there's no problem. That's why I say temperature measurements in the lake or reservoir, the probability function fxy, x1, x2 are identical to each other. The probability of getting x1 and x2 are same. So that is the uh, opportunity when you have unlimited or replacing the number of samples you have. Right, we'll move into the next one is stratified random sampling. Now earlier we went into simple random sampling. A lot of people think a random sampling is good. So simple random spatial sampling is good for certain things, but not good for everything. Because if the variable or the parameter that we are going to sample is randomly distributed over the area, if it is randomly distributed over the area, then a simple random spatial sampling will work. Right? But if it is not randomly distributed, if there are any underlying reasons for the distribution of the parameter that we are looking at, a simple random sampling, spatial sampling will not work. right? So if it is randomly distributed, well, it will give you some kind of valid probability value when you calculate it. But systematic random sampling, it's opposed to the previous one, simple random sampling. So instead of simple, we put systematic. We do it in organized way. Right? I'll give you example. If there's we want to find the number of plants, particular type of plants in a given area, right? So number of plants, what kind of percentage of or what kind of number of plants you have in that area. So you take samples, you go to different locations and see how many, whether there is a plant or not. So suppose all the plants that you are going to evaluate are distributed on one side of the field. One side of the field, you have all the plants. But when you take a random sampling, probably you would have missed that edge where you have plants. So you will take samples, but you don't find that particular plant. So you are saying, I took 100 samples and I did not find any sample that particular plant. So probability of having that plant in this area is 0. But that's not true because it is only found in one side and you have not sampled it properly. Suppose you have sampled it from that side. So you have taken many samples where you have plants and then we are giving that average. Okay, I have 50% of the area having this plant, but that is not true because your random sample covered mostly that area because it's random. So random sampling will not always give results, but when the variable is distributed randomly, random sampling will work. Now, if you look at the systematic random sampling, what we do is to draw a systematic random sampling. Every k element, if it is k, can be 1, 2, 3, 5, 4, 6, 7, 8, 10. Element of the sampling frame is chosen beginning with a randomly chosen point. Right? So for example, if you have 200 areas, 1 to 200 numbered areas. So first area is that area 2, 2, 3, 4. So 1 to 20, we will put it from top to bottom, and then 21 starts from the next column. So every column you have 20 plants, 20 areas. So you have altogether 200 areas and you have 20 into 10 columns. Okay. So consider a population with n equals 200 and we wish to draw a random sample of n equals 10. So we want to take 10 samples. Out of the 200 samples, we want to take 10. Right? So remote sensing also you learn, you have a total area, but then you accuracy assessment, you take samples. You take samples and assess the accuracy of the classification. Similarly, here you have 200 samples, 200 areas where you consider as samples. We want to take 10 samples, 10 areas and investigate and see what are these areas. Now, suppose you have an area 20 by 10 according to this, right? 20 by 10 areas, 200 areas. So what we do is we cannot go and look at all 200. We want to see taking a sample from 200. Say we take 10 and then evaluate the sample 10 and then predict about the 200 samples, predict about the population. So that is what we do. If you learn in remote sensing a method called direct expansion, a method called direct expansion. Did you do that in remote sensing? Yes or no? Hmm? You did or not? Direct expansion method. No? Yes or no? I couldn't hear. Nobody wants to answer. Whether you did direct expansion method in remote sensing.
No, sir.
No, sir.
No. Right. It's a simple method, right? Now, what we do is, if we want to evaluate, say, in a given area, we want to take, say, we have 100 hectares, right? We have 100 hectares. So we suppose it's a rectangular area. So we have 100 kilometers, 100 hectare area. So this side we have 10 hectares, 10 hectares, 100 hectares altogether. 10 by 10, 100. Right? Now, if we want to have this 100, if we divide this into, say, my drawing may not be very good. So if we divide like this and make a gridded structure, right? Like this. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 100, 10 by 10, 100 areas. Right? Now, if we want to take 10 samples, right? 10 samples, and then you can do it randomly. Say, so if you number this 1 to 100 samples, you can take random number. Give me a random number between 1 and 100. So somebody says, okay, my random number is 81. You take 81 sample. Another person says 74. You take 74. Another person says 12. So you take 12 sample. Likewise, you take 10 samples. Right? So your number of samples is 10. From random number, you take 10 samples. Then what do? You look at each sample, because each sample is not a point, it's an area. Right? It's area. If you take, I say 10 hectare by 10 hectare area, 100 hectares. So that means here 1 hectare is 100 meter by 100 meter. So each size is 100 meter and 100 meter. Right? So your size is 1 hectare. So in 1 hectare, you look at what is the area under paddy. right? What is the area under paddy? And all the samples you check, because you take samples mean you go to the field and see that area. So if you look at each and every sample that we take out of these 10 samples and look at how much paddy area is there, because each box now, what is the area of each box? 1 hectare, right? 100 meter by 100 meter area. So each hectare, what is the percentage of, what is the amount of paddy land you have? So in first hectare, you have 300 square meters of paddy, right? Second one, how much? Third, out of the 10, you total, right? And then suppose you find out of the like 10 samples, means you have taken 10 hectares. Out of the 10 hectares, you find 3.5 hectares as paddy. Then you directly expand it. Okay, 10 hectares as 3.5. What is the paddy area if it is 100? Right? If 3.5 in 10, how much paddy is in 100? So you simply say you have 35 out of 100, right? Directly expand. So we do, when you don't have remote sensing data, when you do the field investigation, so we take a sample and then directly expand it to the entire area. So if we take a representative sample, and if the variable is randomly distributed all over the area, then your answer is not very much away from the reality. Because when you make a guess, when you make an estimation, it's not 100% sure. If you want to get it 100% sure, you need to go and inspect the entire area. So if you take a sample, and then what you do is, we get the inference from the sample about the population. We take a sample and we assume that entire population is like this sample. So we make inferences from the sample so that we can make a good prediction. So sampling comes when it is not possible to cover the entire area. Now, when it is census, you don't need samples, because census is covering the entire population. So if you look at the household and expenditure survey conducted by the Department of Census and Statistics, those are census. You go to each and every household, collect the information, right? But if you take a sample and evaluate the sample and predict about the population, then you need to get a proper representative sample and make inferences about the population. So that will depend. There is a component of uncertainty. We introduce it as error. So we need to work on that part if there is any uncertainty. Okay. Now, if we go to systematic random sampling, earlier we did random sampling. So what we do is random number, we take a sample. But systematic sampling, we don't do that way. We have a systematic way of getting sample. So if your sample size, population size is 200, capital N is 200, and we want to get 10 samples, simple N is 10. You divide 200 by 10, your answer is 20. That means every 20th point is sampled, right? So every 20th point is sampled means it has a systematic way of sampling. But there's a random component also. It is systematic random sampling. So first, right, between 1 and 20, you take a random number, right? 1 to 20, random number. So say number is 5. So you take the fifth sample and then you take every 20th sample from 5. So you take the 5th sample, you take the 25th sample, you take the 45th sample, you take the 65th sample, you take the 85th sample, likewise until you complete your total number. So that is, you take every 5th. So 5th, 25th, 45th, 65th. So likewise, you continue. So that is as a systematic component built in on the random sampling between. So if you take a random sampling between 1 and 200, it is totally random sampling. But we are not doing that. You take 200, divide by the number of samples. Now every 20th, we take one number between 20 and 1. So this is called systematic random sampling. Why is it a systematic random but not simple random? Available choices are only 20. If it is a random, you have available choice of 200. So when you do a systematic random sampling, your available choices are significantly reduced. And then it says periodicities, regularities are picked up by systematic random sampling. So random sampling will help you to identify a periodicity. If something is happening after a certain periodicity. We call periodicity if something is happening in periods, right? In periods. Like in the school, we have periods. It's happening every day in the same periods. Likewise, you have a certain period in which it happens. Or regularities. If you have a regular way of happening things, you can identify by using the systematic random sampling. Some examples exist in time sequences or in regular spatial intervals. So spatially, you can take regular spatial intervals, or you can take intervals in time when you take the samples. Same place, you can have different time intervals. That is spatial temporal sampling. Spatial sampling is same. You take different spaces. So if you combine both time and space, you call spatio-temporal samples. You understand what I meant? So you can take samples at different times. You say, I'll take samples every day up to 30 days. So that is continuously you are covering it. Or you can say, I can take sample every 5th day. So you take 5th day, 10th day, 15th day, 20th day, 25th day, and 30th day. So likewise, you can divide. But before doing that sampling, you need to check for randomness. Because if it is a randomly distributed variable, you don't pick up in a systematic random sampling. If it has some kind of pattern, then you can identify it through systematic random sampling. Okay? Any questions? Can you think of any example where systematic random sampling is better than simple random sampling? Any real world example? I'll give you 2 minutes to think. Example for systematic random sampling, where systematic random sampling will produce a better results. Okay. Anybody has example for which gives the systematic random sampling give you a better results than random sampling? Right. Okay. I will explain now. Suppose you look at this, right? This hypothetical example. A is tea plantations, B is rubber plantation, C is, say, coconut plantations, right? Now, without surveying the entire area, right? Without surveying, like suppose we have the length here is 10 kilometers and length width here is 10 kilometers. So we are looking at 100 square kilometer area. We are looking at 100 square kilometer area. And we want to know how much area is under tea, how much area is under paddy, how much area is under C. We don't know these lines where it demarcates. We have no idea. Right? So if you want to cover the entire population, you have to travel to this 100 square kilometer every inch of the land to check what is there. Right? So you need to visit and do a survey. If the people ask you to produce a map of tea, paddy, and coconut plantations, then you have to take your surveying equipment, go there and identify these lines where are the boundaries of tea plantations. So it's a surveying job. You go and you take your surveying equipment, go and find where the boundaries are. Right? So if your field surveying is not an option, to find the map, identify the area of plantations, what are the other methods you have learned? You can switch on your microphone and answer. So if you, as most of your survey, so if you ask to draw a map of this area showing different tea, rubber, coconut plantations, you would go and survey the entire area. That will take, if it is 100 square kilometer area, that will take couple of months. Okay. But there may be other methods where you can do this easily. Can anybody give me a method to map this ABC areas properly? What can we do?
Drone survey.
Hmm?
Drone survey.
Yes. Okay. You can do a drone survey or whatever the method. What you can do is take an image of the area and classify it. Right? Take an image of the area or get a few images and get the fused image and then visually demarcate, because you can see it's different, so visually demarcate the boundaries of each plantation. Right? So would that save time? Yes. But then it needs some other inputs, like you need an image or you need to have a drone mission plan for this. right? You need to have some investment. Or you have to take a satellite image and specify it. That's also possible, which may be less costly than organizing a drone mission. Right. Now, these are the options you have. If somebody asks you, I want to have a map of this area showing the boundaries of each plantation. But most of the time, what they ask is not a map, but the data, statistics, right? So they want to know what is the percentage area under tea, what is the percentage area under rubber, what is the percentage area under coconut in this area, in this land. Now, you don't have to go for mapping in this because you only need the numbers. You only need the numbers. So if this kind of situation, if you use the systematic random sampling, you will be very accurate in assessing the areas under each plantation type. Suppose you use random sampling, total random sampling, you take random sampling and you get more samples on this. More samples you have taken randomly area, and then when you evaluate, you overestimate the coverage of B compared with A and C. But if you use systematic random sampling, what you do is you take one place and then equally spaced places, you take samples. So then you can get a fairly good idea about this. Right? For example, you take the samples and take samples at, say, you start from here randomly and take sample, and then you take the same spacing sample along the line, and then you go and take samples here. So you get much better accurate results of the actual situation by doing this kind of sampling. But remember, sampling always include certain level of error. We call it as sampling error. By doing proper sampling, we are trying to minimize this sampling error. We are trying to minimize the sampling error. So it's asking the question, why is it a systematic random but not simple random sample? Because available choices are only 20. If it is random, you have 200 available choices in this particular example. So you can do this sampling, spatial sampling, along the spatial dimension. And also you can do sampling on the time dimension. You take every 2 days a sample. That is a systematic random sampling because you take the sample every 2 days. Right? First week you select randomly a day. and then every same day you take the samples every week. So that's your systematic random. So likewise, you can produce some better results when you do systematic random sampling, depending on the distribution of variables in your sample. So first of all, whatever the sampling method you use, you need to have a good understanding about the parameter that you are going to evaluate. Without knowing that, it is very difficult. So you need to have a good idea what you are going to sample. And you need to have that background information. Then you can decide what kind of sampling. So first of all, remember we do sampling. Here we talk about spatial sampling. That is done when it is impossible to cover the entire population. When it is impossible to cover the entire population, you take samples. When the land that you want to uh, get samples, because when you cannot visit the entire land, when you cannot do a field survey covering the entire area, you go for sampling. Right? When it is not possible to get each and every item in the population assessed, then you take a sample. So when you have sample, you introduce an error which is called sampling error. Which is called sampling error. Depending on the total number of areas and then depending on total number of samples we take, we can estimate not only the uh, area values, but also we can look at the sampling error. The errors that you could exist that you can find in the data of the sample. Right. So we go to the next one. Next one is called a stratified random sampling. So it's again, the first one is total random sampling. Second one is systematic random sampling. Still random component is there. This one, a stratified random sampling. Right? So obtained by forming strata or classes in the population and then selecting a simple random sample from each. So your sampling strategy is random, but you find this random sample from each layer or each strata when you stratify it. Now, stratification is process called stratification, stratified. Stratification is identifying the layers. Say, for example, you want to find the people income of individuals, income of people. So if you go and ask only the males, if your sample comprise of male, they are generally little higher paid than females, right? Some of the jobs. So if your sample is predominantly male, you will have a bias in the data. Right? So therefore, we want to have separated the males and females. This stratification, we have two layers, two stratas. One is the male layer, other strata is female. Right? Similarly, you can have uh, older people, middle age, young people, small babies. Again, stratification. Why we stratify? We want to have each of these categories represented in the sample. We want to have each layer of different groups included in our calculations of the uh, area under a particular parameter. So stratified random sampling. You first identify what kind of parameter you use for stratification. You use gender, male, female. You use age, old, middle, young. You use skin color, brown people, white people, black people, whatever. What's the parameter that you want to? So stratification, how do you identify a strata? That starts there. So first of all, when we want to do stratified random sampling, first stage is what is the basis for stratification? What is the basis for stratification? Now, once you identify the basis for stratification, then you can identify the strata and then go for random sampling. Right? Okay. I'll give you 3 minutes. Each one of you think of an example where you identify this is my stratification, this is my strata, then you can go for random sampling. So you want to first think of what is the topic. Okay. For example, I am going to do a forest inventory, right? My topic. Then what is the basis for stratification? You put the next line, what is the basis for stratification? So what is your project criteria? And then what is the basis for stratification? Think of example where you can do a stratification, stratified random sampling. So give what you're going to estimate and then give what is your stratification strata levels, right? Send me a message. I give you 3 minutes for you to think and give example. I want everybody to think and give me example. A project. So for example, I want to do a forest inventory. What is my stratification, right? So I want to have my stratification based on wet zone, dry zone, intermediate zone, likewise, right? So if each one of you, I'll give you 3 to 4 minutes, think of example and send it. Okay, I will take each, some of you have sent your answers. I will take your examples and then explain how it is relevant. Okay. Now, first person, um, Pulavan said high forest, low forest. And so we don't know what is the objective of your sampling. Without knowing, I cannot comment high forest, low forest. High and low are proper stratifications. You understand? So I should know what you are going to sample, what you are going to measure. So without knowing that, I cannot say high and low is a correct stratification. Okay. Go to the second person, Nishanka. Right. Topic is urban planning. And then you have residential, commercial, industrial, and agricultural. Okay. We want to do get some data for urban planning. So you divide the areas based on the use, whether it's residential, commercial, industrial, or agricultural. Say, for example, it would have been much better if you take like uh, taxation purposes. Then you divide residential, commercial, industrial, which has different strata to identify. So, next one, employees of the company. Karunaran. That is not an spatial example, right? We are talking about spatial examples, which is it's not employees of the company based on the department. It's not a spatial example. Raghunathan says estimating tree density or species diversity or biomass, right? I don't know what you are going to estimate, so I cannot say what you have. Topic is estimating tree density or estimating species diversity or estimating biomass, but you should tell us what is your stratification. We have not given that. 24087. So your example, students' attendance, primary, secondary, advanced level. It's not a spatial example, so I don't want to comment on that. Then Gobinath says, persons cause motorbike accidents, adults, middle-aged, elders. That's also not a spatial example. And then Cruz, school, male or female, grade level of education. It's not spatial. Project how university student satisfaction with online learning. Starter 1 years of study. Starter 2 faculty. It's a Jayasuri. Although it's not a proper spatial example, I would accept this because you can look at it, how university students like or how students perform on online learning, depending on the number of years and then based on different subject areas, different faculties. It's not a spatial example though. Next one, Samaravira, tea estate, strata, age of bushes, type of clone, topography, type of soil. Well, tea estate, the issue is what are you going to evaluate? Your first line should have what are you going to evaluate? Yield, then you should have different types of clones, right? You can see different areas under different topography, different soils. So it should be the yield, okay? And the next is Kavipriyan. Project is start a manufacturing company in a village. Therefore, need to find laborers in the same village. Strata completed the ordinary level, completed advanced level. not a good spatial example. Topic agricultural land productivity with irrigation type. Okay, you are going to find different areas land productivity, agricultural land productivity based on rain-fed, uh, canal irrigated, and the tube well irrigated. Yes, that you can see. You can see the yield in differently irrigated areas. So different irrigation types applied. So that's a good example. Good, thoughtful example. And next is that was from Ishani. Good example. And then next is Jayawardena, PD and Jayawardena, trend of moving to cities, strata occupation. Right? Now, you should define what your strata is. Occupation. Okay, how do you define it? And then based on the uh, occupation, so it's basically you are identifying individuals. So then it is not a spatial example. Next one, Vikram Singh, topic market research for soap users. Population, Colombo district, stratification on socio-economic class. Uh, your topic is not spatial, although you take the sample from socio-economic class and which is also a people. So it's not a spatial example, but it has a basis. Your basis is perhaps right. Sudarshan estimating cultivation of paddy in different types of seeds. So your cultivation of paddy in different types of seeds. I don't see that that's a valid information, because if you look at the yield of different types of seeds, that you can understand. So estimating of the differences in yield by looking at the stratification based on different types of seeds used. That may be a valid example. Vasanta, land use planning, built up area, forest, vegetation, water. For what? Land use planning, built up area, forest, vegetation. So its topic is not clear. What you are going to evaluate, it has to be more specific. Distribution of marks for maths in grade 11, that's not a spatial example. So I don't want to comment on that. It was from Vani Nayak. And Mahadeepan, University of Students, Masters, PhD extra. For what? Masters, PhD. So it's not clear. Next one is coral reef health monitoring. So what is your strata? Not given Chaturanga, Lahiru Chaturanga. Kajentiran, urban area, residential, commercial and industrial. Not given the information properly. Bimsara, rice lands, high, moderate, low yields. For what purposes? Your purpose is not very clearly given. So what is your topic of the work and then how you do it? So this is some of the examples you have submitted. And so that shows, you have basic understanding. Most of you have basic understanding. Some of you cannot think of spatial examples. And then uh, others, some others have not really understood, because we have tell what is your activity that you want to have strata for. So if I want to see what is the preference of people for say, action movie, and if I stratify the area based on low rainfall, moderate rainfall, high rainfall, that doesn't have any meaning, right? So your stratification should have some kind of relationship with the variable that you are going to assess, or a variable should be dependent on the strata, have some relationship with the strata. I'm going to estimate the tea yield in Sri Lanka. Look at low country, intermediate country, and the high upper areas. So that is example. High, low, medium elevations. I'm going to estimate the yield. So then it is going to be different in each of the strata. That is the idea. I'll tell you now the basic idea of strata, right? Obtained by forming strata or classes in the population and then selecting a simple random sample from each. Population is divided into strata. Each member should appear once and only in one class or one strata, selected randomly in each strata. Social surveys often stratify population by age, income, location, or residence. Properly organized stratified sample can reduce sampling error, require homogeneous strata, less internal variability, should know relationships between characteristics of the population and problem being analyzed. So when you go for stratification, basic idea is you have to have within strata uniform condition. It should not vary. But among strata, you should have some kind of a difference. If if there are two strata, both are same, there's no point having stratification. So within strata, you have to have low variability. Among strata, you have to have higher variability. So that is the condition. If you look at the yield if you want to evaluate the yield in seedling tea and the vegetatively propagated tea, you know that yield is different. So seedling tea will have a reduced smaller, little lower yield, and the vegetatively propagated tea will have a higher yield. So that is the basis for classification. So if you have divided into strata and look at it, then can be estimated more accurately. So whenever you do sampling, you have a sampling error, and sampling error can be minimized when you have a proper stratified random sampling. Because random sampling, your sampling error is high. And when you go along for systematic random sampling, you can reduce that random error to a certain level. By going into stratified random sampling, even you can have a less sampling error. So that is the idea of going into this kind of a sampling. And there's another type of sampling called cluster sampling. And population is divided into exclusive and exhaustive classes. Actually, it should be exclusive and exhaustive classes. These classes are clusters. Either take full cluster or take a random sample from clusters. Each cluster should be as heterogeneous as possible. Now, this is opposite to strata. Strata, we have to have a uniform level. Say, if you say elevation-based strata, low country, you have low elevations throughout the area, it is low, right? But in cluster, it has to be heterogeneous as possible. So basically, it has to be having everything. Totally opposite of stratified sampling. Cluster sampling often can give poor results. Arbitrary or randomly defined clusters are unlikely to be representative. Sampling error in clusters is higher than random or stratified. Here, sampling error is higher, but it is time and cost efficient. Ideal when population sample is geographically dispersed over a larger area. So, cluster sampling, and this is an example of cluster sampling, which is the below figure. Upper figure is stratified random sampling. You divide into two stratums, stratum 1 and stratum 2. You take random sampling from each strata and then you make your sample. Second one, you have, rather than strata, you have clusters, and you take entire cluster into the observation. So you can do a cluster sampling. You make clusters which are not homogeneous. It should be heterogeneous as possible. Then you take a cluster, and combination of clusters will make your sample. But remember, cluster sampling will have higher sampling error compared to the stratified random and uh, strat, uh, stratified random and the systematic random sampling. So I hope you understand the difference between clusters and strata. So in terms of efficiency, stratified random cluster is order. Stratified are more efficient, random is less, cluster is even less. Stratified requires least samples and cluster requires most. A mix of all three is also possible. Now we go for other option. I explained a little bit earlier this example, geographic sampling. Now, I took from the example of John C. Taylor's example. We have an area, right? We have a geographical area. So you can see the geographical area with this boundary. Sorry. So you have the boundary of geographical area. And then we want to look at, for example, what is the land use of this entire area. So I told you earlier also, if you want to have land use mapped, that's a different story, right? But if you want to have a land use as a value, right? What you can do is you can take some samples. So this is a sample unit, 1 square. And then say what our observation is from this area, right? In this area, we have different land uses, right? Different land uses. But we want to estimate what is, say, it's a Kurunagala district. So this is the district boundary. We want to have what is the exact area, right, of paddy in the Kurunagala district, right? But we cannot find exact area unless we do a complete survey of the area. We cannot find this. But we can get a fairly good idea if we take some samples and then each sample, if you select sample areas, visit those sample areas with the GPS and then mark the area under paddy. So take your surveying equipment, go to each area, then measure the area under paddy. And then if you take the first sample, your area under paddy is, sorry, C1, C2, C3, C4, and you have n number of samples, right? We have n number of samples. And then what you do, you have n number of samples and in this n number of samples, you have paddy of each area this much. So you add all n number of sample paddy areas. So you have a total paddy areas in n samples, right? You have each area, you have the paddy area. So you add these together, get the total of paddy in the n number of samples. Now our issue is if n number of samples or if each area is this much, you have n into this much area. If you have paddy, for example, if you have paddy of this much in n number of samples, what is the total paddy extent in the entire area? So if you know the sampling fraction, if you sample the entire area 2% and get the paddy area multiplied by 50, you get the 100%. Is that clear? So this is the method that we called as direct expansion. You do a sample survey, from the sample you expand, because as a surveyor you cannot cover the entire area. So you cover only 2% of the area, 2% of the area sample, and then expand it to the entire area. This is called direct expansion. Right? So in that method, your accuracy, there may be issues because you only look at 2% of the area. You have not looked at the other balance 98% of the area. Right? Therefore, your accuracy level may be considerably low because your sampling fraction, sampling percentage is only 2%. If you increase it to 5%, 10%, you get more reliable answer. You get a more reliable answer if you expand it further. Right. Now, that is where we use supplementary data for direct expansion. Right? Supplementary data. Supplementary data is coming from, say, satellite data or drone data. You get image. You get image. And then, say, for example, you look at one area in this sample, 2% sample you take, and in that area, inside, you find certain area under paddy. You take the image, you identify that area, you extract the characteristics spectral characteristics of that area. And take all the examples, wherever you have paddy, you extract the spectral characteristics of the area. What kind of pixel values you have, right? What kind of pixel values you have. Then you do a classification by using those data as training data and get the entire area classified. That's having a much higher accuracy than direct expansion method. Right? So that is where we use satellite data. When we want to map, we use the data. Even when we want to take statistics, you can get much improved version of statistics, much improved assessment by having satellite data. Any questions from here? Then once you have the data, you can plot that data on this kind of a graph and show how the data are distributed. Okay. I had a power outage. Okay, since time is up, I will stop here and I will continue from next week. I have a problem in sharing the slides. Right. Okay. Can you see the slides?
No, sir.
All right. Okay. We will stop here for the day and continue from next week. I will show you again this slide. I have a problem in I have to reboot the machine and come back. Okay. Right. So we'll stop here. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.